Okay, so limits. I need to introduce you to a colleague of ours. This board is, 304 is a little different board than the other boards. 304 was specially designed, so it includes, within this two-dimensional realm, it includes some creatures called calculus ants. Calculus ants are point-like. Calculus ants crawl around on functions, and they have some adapted senses that are important in their two-dimensional world. Calculus ants can sense their coordinates in the plane. Okay, so as an ant walks along the function y equals x squared, for example, when an ant's x value is -2, what would it sense as its y value? 4. Yeah, good, 4. Okay. Limits are particularly useful in situations where you've got either a calculus ant that is blind and it can't see where it's going, or in rare cases, sometimes very dense calculus fog will roll in and ants can't really see where they're going. In both cases, limits are important to us. Limits mathematically describe values of a function, predicted values of a function. Okay, so this is a really important statement I'm going to make that we'll echo again and again. Limits don't have anything to do in a direct sense with the actual value of the function for a given x value. When I say value of a function, I mean y value, right? Okay. Instead, they always deal with the predicted value, right? And the name kind of implies that. A limit is telling us, it's not saying precisely, but if we do something, what is the projected outcome, right? It's not, so for example, as an ant, let's say a dense calculus fog rolled in, and an ant were walking along this function, either from left to right or right to left, and he were approaching an x value of -2. What value would he anticipate stepping on? 4. He would, wouldn't he? Because as that ant walks along the function, let's just say that's, this isn't drawn to scale. Let's say that's -2, and it doesn't matter what's actually there, right? As the ant walks along the function, he senses that his y values are getting, bigger and bigger and approaching that value, right? And so he's going to say, well, that's logical. I mean, as I get closer and closer to -2, my y values are getting to be something like 3.9, 3.99, 3.999. I'm approaching 4, right? And he anticipates that's where he's going to step. Same thing would happen if an ant were to approach from the left. His y values would be diminishing as he approached x equals -2, and they would be approaching from larger values of y, they would be approaching the value 4, correct? Okay, no big deal. So then we could write this in math. Here's our notation for this then. The way we express this mathematically, this idea is the limit of the function x squared as x approaches -2 is equal to 4. Okay? Because that's the value that the ant anticipates stepping on, right? Okay? Fill in the blank. The limit of x squared as x approaches 0 is 0. Good. Okay, let's take a different function. Very similar though. This is the function f of x equals x squared. Okay? What about the function instead? Let's take the function f of x equals x cubed over x. Okay, algebraically, what's that equal to? X squared. Okay, could cancel like factors, right? There's something different about it though. what's the domain of values associated with this function? All reals. Yeah, how do you know that?
Because there's
Okay, it's a good question, and we'll come back to this a lot. This is just today. Don't approach this today as though there's some real specific outcome. Yeah, you're going to learn what a limit is, but a lot of this is us just kind of getting our feet wet again and sort of talking math. When we talk about the domain of a function, we're trying to find all the values of the independent variable of x in this case that work for that function, right? When we're trying to find all the values that work, really the places that are interesting are the places that don't work, right? The default setting is they all work. In what cases would a function have a problem? Where would you have a domain that would have to be restricted? Where could you possibly get values of x that would not be okay in a function?
With the denominator of 0.
Okay, so one thing you can't do for real numbers is you can't divide by 0, right? Okay, so that's one no-no that we got to look for. Any value of x that would cause us to divide by 0 has to be excluded, and that cannot be a part of the domain. It's against the law, right? One other thing. Remember the other thing that could happen. This is a little stranger, maybe.
Would it be imaginary?
Okay, yeah, what distinguishes a complex number with an imaginary part from just a regular old complex number with all real parts?
The square root of negative.
Okay. Yeah, we can't take a square root. In fact, we can expand that. You can't take an even root of a negative number, right? So those are the two no-nos for real numbers. You can't divide by 0, and you can't take the square root of a negative number, or an even root of a negative number. In both of those cases, any values of x that would cause one of those two violations to occur would have to be excluded, right? Okay? So we said the domain up here then, the domain is going to be all reals. Negative infinity, right? Okay, what about down here for this function? Except 0, right? Because 0 can't exist on the bottom, right? Now, what if I wanted to graph this thing, though? If I wanted to get an idea of what the shape of the function is, we could simplify this algebraically to the function x squared, right? And does that seem like some hand waving here? Does it seem like I'm just, where'd that come from? Think about it in terms of specific numbers, and you can pretty readily convince yourself that's going to work. If I were to take, for example, a value of x equals 4, right? If I plug it into this function, let's call this one, you know what? I shouldn't call this f, because we've already defined f, and that was different. Let's call it g. How about? If I evaluate f at 4, I'm going to get what? 16. I'm going to get 4 squared, right? If I evaluate g at 4, I'm going to get 4 cubed divided by 4, which is just 4 squared, right? That's going to be that way. 4 is not special. It's that way for any number, isn't it? Right? Except 0. We can't use 0, right? So if my domain is going to be restricted, my domain is now going to be, how can I say that?
including negative infinity to negative 1.
Would it be 0 with a bracket?
Oh yeah. 0
Okay,
not
so-
including 0.
So we could do this. We could say we want to use rounded brackets because those don't include values, right? And you always have to use rounded brackets with infinities because infinity is not a number, right? You can never get there. Does that make sense? So we go negative infinity to 0, comma, 0 to infinity maybe? Something like that. Got an easier way. How about that? Okay, that implies everything except that one value. Now, what's the graph going to look like?
Essentially the same.
Essentially the same. Okay, I'll start by drawing the very same graph, but what do I need to change?
One single pixel.
Yeah. What about that single pixel?
You can't touch
It doesn't exist, right? The function is only defined on its domain. So is the function defined at 0? No, it's not. It's not defined there. So we've got to do that. You know what we call that? Call that a hole.
Circle.
Oops, come on. The function has a hole.
So, when we were graphing that for a problem, would we label it as such, or just put a circle?
Just put a circle, open circle. Yeah, that's the terminology associated with that. But we recognize that to be the single point that's omitted from our domain, right? Okay, here's the $1 million question for the day, though. Here's what I want you to tell me. On this function down here, I'd like to know what is the limit of g of x as x approaches negative 2? Actually, that's not the $1 million question yet. 4, right? Makes sense, right? As the ant walks along the function towards an x value of negative 2, the ant anticipates stepping right there, right? Agreed? Okay. So the answer is 4. Okay. What's the limit of g of x as x approaches 0? Talk to me about that. What you're thinking? Would it skip it? The function does skip it. Okay, but somebody remind us, what's the definition of a limit? It's the anticipated value.
So it would just be
So
zero.
it's 0, yeah, and that is the answer. The answer is 0. Because this, I think this really illustrates this bizarre nature of a limit, that the limit, it doesn't really matter what actually happens when you get there. That is not what the limit is referring to, right? It's the anticipated value. As the ant approaches 0, x value of 0 from the left or the right, doesn't the ant anticipate stepping on the point 0, 0? So that's the limit. Weird, right? You get it? Okay. What if we change this and let's draw kind of a more bizarre function here for a second. How about if we do something like this? Okay, so here's our function. I guess I probably need call that 1, that 2, how about? Whoops. Like color. What have I not done? Okay. There's my relation. It's a function. I function out.
Is the black hole have any significance?
No, it's supposed to be, no, it's supposed to be blue.
Just
Okay, so I'd like to know what's the limit of f as x approaches negative 2. Now, don't say anything. Everybody think about that for a second. When I ask for a limit, am I asking about an x or a y value for the answer? Good, it's the y value. Good, good. We got that. Good. What do you think?
Is it dictated by which direction you go?
Well, you tell me. If an ant approaches from the left or from the right, is that going to change your answer? What's it gonna be?
Just one.
1, everybody agree? Yeah, he thinks he's stepping on y equals 1. Does he step there? No, it's irrelevant, doesn't matter, right? Okay, what about the limit of f of x as x approaches 0? Yeah, does the function exist at -2? It does. It's got a value there, right? It's supposed to be 2. It's got drawn a pretty crappy drawing, but you get the idea, right? Okay, but the limit was 1. Does the limit exist at x equals 0? No, it's got a hole in the function there. But the limit is still 1. The ant still anticipates stepping on 1. Agreed? Okay. What about, okay, what's the limit going to be as x approaches -1? Or do you see an issue? Yeah, there is an issue, isn't there? This time, an ant approaching from the left is going to get an answer of what? 1. An ant approaching from the right is going to get an answer of 0. Okay, so that's a problem. Later on, we'll have a specific way of addressing that problem and still get and still attaching a limit to that. Okay, but it's going to have to be more specific. But for now, the way we're broadly defining a limit is that, okay, it's the place where an ant anticipates stepping, but for the limit to make sense, the limit has to be the same for 2 ants approaching from opposite sides. Okay, so what we'll say for now, what we'll say about this one is no limit. Okay. Later on, this will give you a little bit of a preview of things to come. We'll say, okay, well, by limit, we mean a 2-sided limit. Okay, so later on, maybe we'll look at more specific 1-sided limits that still could exist, right? But for a regular old 2-sided limit, when we say limit, it always implies a 2-sided limit. That doesn't work. What about at the limit at x equals 2? Same situation, no limit, right? Okay, so that tells us one thing that we just established. You have good understanding, we get what a limit is, but we have problems when, like here and here we had problems because there's a break in the function, okay? So if we wanted to establish some kinds of places, some topographical places on a function where limits don't exist, one of them is when there's a break in the function. Okay, limits don't exist there. How about something like this? What if I draw the function how about if we take the function f of x equals what's that look like? Go back to last year, what's that look like? Remember? What's the domain? Okay, so x can't equal 1, right? Okay. Does that immediately give an idea what that looks like? Inverse function? If you don't, that's okay. I'm just kind of trying to figure out what you know about that. It's not leaping out at you. That's fine. That's fine. I'll graph it. We're going to have a really good way soon to be able to sketch a graph of that. Okay. Here's what it looks like. What's going on at x equals 1? What's that function doing? Where is it going? How far down does it go here? Infinite. How far up does it go there? Infinite. Yeah. Okay. Okay, so what do we, remember what we call that? Asymptote, yeah. So we've got a vertical asymptote at x equals 1, infinite division in the function, right? What do you think is going to go on here? What if we want to do something like the limit of f of x as x approaches 1? It is.
Wouldn't that be, yeah, still be.
Clearly no limit, right? And it's a break in the function, right? It's a huge break in the function. Okay, what if I do this though? That changes the function pretty dramatically. I don't know if that's. There we go. It's actually going to change. What I'm doing is a little bit hokey because it changes it in some other ways too. It's going to make it a little bit more squared off. So I'll do that. I don't want to be hokey. So it's going to look maybe more like this. Okay, but let's just call that f of x. What's the limit? Okay, you could say infinity, but infinity is not a number, right? No limit, right. This time, is it because there's a break in the function? That's a tough one. I mean, yeah, you could argue that. It's not obvious though, right? Previously, it was pretty obvious there was a break in the function. But what's going on here? Think about this. Think why the answer infinity doesn't really work for us. Remember what we said about a limit. A limit is the place that the ant anticipates stepping on, right? So as x approaches 0, does that ant ever see a place or sense a place that they're going to step on? Very different behavior from what we had before, isn't it? If we look back at these examples, the ant was able to, it's clear that we're approaching a value of, 3.9, if he's moving from the right, 3.99, 3.999, 3.9999, right? I mean, it's approaching 4, right? The increments, the y increments, what's happening to them as the ant approaches -2, what's happening with each step as he gets closer to, I want to say this, as he approaches -2 more closely, using smaller and smaller steps, right? Like if I'm approaching the door, let's say I'm going to cut my distance to the door in half every second, right? So there's 1 second, 2 seconds, 3 seconds, 4 seconds. My steps are getting smaller, right? Does that make sense? Same thing for the ant. His steps are getting smaller. And wouldn't you agree that the corresponding steps, increments of y, are getting smaller? And it's definitely approaching a discrete value, okay? What about here, though? Yeah, in fact, every step he takes from, let's say he's walking from left to right, every step that the ant takes towards 1 makes the hill steeper, right? No matter how small he makes those steps, the y increments are going to be growing, not shrinking, right? Does that make sense? Think about it from the ant's perspective. All he sees in front of him is this peak that's just infinitely high. No matter what he does, he can't make any progress. It doesn't stop, right? So this too is an example of no limit. What's the reason this time? How would you describe that? There's a bunch of good answers for this.
Which will never hit 1.
Okay, so how would you describe, you'd say, okay, this is a case, last time it was a case of a discontinuity in the function or a break in the function. To be continued. If you got a Chromebook out there, why don't you stick it back in the cart?
Would I be able to leave my books in here and then pick them up for physics?
It's fine with me.
Yeah.
I just,
Like,
I don't think anybody's gonna mess with them.
Okay.
Yeah.
Thank you.
There's a chance, but I don't think
Yeah.
anybody will.
Yeah. I'll roll the dice.